Welcome back. So today we are going to discuss about the dating part, as I have mentioned in the previous lectures also, that dating is again one of the most important aspect if we are trying to understand the time frame of the evolution of the landscape, and also the events, okay, like climatic events if we want to bracket, or the tectonic events also. So these are the best technique, okay, and one of the best technique which is available is the optical stimulated illumination, because this gives more precise age as compared to the other dating techniques. I don't say that this is the only best, but I would say that one of the best technique which is available. So we have been using EMS also, that is accelerated mass spectroscopy, that is based on you using carbon or like charcoal, or you use the buried roots or any old stuff which comprises carbon, that can be dated with that what we call the C14 dating actually. Now coming to this part, let us have a brief discussion, and as I have also emphasized in the previous lecture, that this will be followed by a lab. Okay, so we will be having the lab visit. So let's see what exactly is the optically stimulated illumination, and short form that we call this as an OSL dating. Okay, so the development of illumination, if we go back, then initially it was like thermal illumination dating technique. TL was first developed by Atking in 1964, and initially it was applied to the archaeological sites, okay, and mainly to obtain the firing age of the ceramic material, or you can say the potteries. Okay, but later it was been thought of that why can't this technique be applied to other fields of geology and earth sciences. Okay. So then David Hutney and his colleagues, they found that TL dating technique could also be applied to sediments, and since quartz and feldspar could be set to 0, that this I will come to that what exactly we are talking about set to 0, but they found that the quartz and feldspar are the most abundant minerals which are available in the sediments and can be used as a part of the measuring the illuminations stored within it. Okay, and so actually zeroing, I'll briefly tell, this is also termed as bleaching actually. Okay, so when the sediments are exposed to sunlight, then whatever the energy was been stored when they were buried will set to 0. So all illumination has been completely wiped off, and that is what we call bleaching. So whenever, so this sediments can be like I would say that can be used again and again, and it can be used as a clock. Okay, so it will when it get buried, it will keep acquiring the energy, and that energy is been stored in form of the illuminations. Okay, so quartz and potash feldspar, that is both are silicate minerals, comprise typical lattice. Okay, and this is what we call the charge defects. So this lattice depends again on the crystal form. Okay, and this lattice are usually formed during the crystallization process when we talk about the eruption of magma, or the lava flow and all that. Just the cooling effect, that is what the process of crystallization is. Okay, so these two minerals of silicate family, they have good lattice which can store the energy, and when they are artificially like what we call stimulated, they will release the energy stored in form of light. Okay, so this led to development of optically stimulated illumination dating technique in 1985. So this is not very old technique which we are talking right now. Okay, now of course it started way back, like in more than 50 years, 60 years back, like in 64, but now the OSL is not very old one. Okay, so illumination dating, basically what we talk is that amount of light, that is your illumination, emitted from mineral grain like quartz and feldspar when stimulated by a beam of light is used to determine the elapsed time since the sediments were buried after deposition. So, this will give you the time of burial, and that is what we call time of deposition, depositional age. So, after the deposition, how it will keep acquiring the charges, okay. So, or the energy. So, quartz and feldspar, they act as a dosimetry, okay, recording the amount of radiation to which they are exposed during burial. So, here the exposed does not mean that they are exposed to the environment, they are buried, but they are exposed to the radiation, because the earth material is radioactive. Okay. So, from that surrounding material they will keep acquiring the radiation. Okay. So, when they are exposed to those material, they will keep acquiring them. So, once the sediments are eroded, transported and deposited, that is by whatever the action you take, wind, water or ice, and subsequently buried. Okay. So, once this is the process, like you have eroded, transported, deposited and finally buried. Okay. So, buried, they are away from the light, and this is basically we are talking about the sunlight, okay, or any artificial light also, but they are away from that, they are but they are exposed to low level of natural radiation, which has been like in form of alpha, beta and gamma from the surrounding sediments. So, this is what exactly the exposed to radiation is. Okay. So, they are not acquiring the energy from the natural light, but they are acquiring the energy which is what we call the low level of radiation from the surrounding sediments. This is what we are having, the radioactive material. So, radiation comes from the decay of radioactive elements, and these are the elements like uranium, thorium, potassium and rubidium. Okay. So, these are the main minerals the radioactive elements which enrich the energy, or they allow the sediments to store the energy. So, this is what the energy is coming from the radioactive elements mainly. So, now when these crystals are irradiated, that is again by the radioactive material, okay, part of the radiation is released and rest will be trapped. Okay. So, basically what we are looking at is the trapped charges, okay, in the lattice. So, when such crystals are heated, so when you this is again we are bringing into the laboratory and artificially heating them, the stored energy will be released, okay, and that will be released in the form of light, and the process what we call is thermal illumination effect. So, luminescent dating is basically categorized into two. One is thermal illumination dating and another is optically stimulated illumination. Okay. So, these are the two categories we have. And on OSL in particular, in OSL is a measurement of trapped charges, okay, concentrated in mineral grains and determination of the environmental dose from the surrounding grains. Okay. So, this is what we call, that is what we try to get the DE, that is dose, and then another is the dose rate. Okay. So, these are the two parameters we will be generating. I will be coming to this further, how we are going to get this two part. Okay. So, now further little more information about this, that when we calculate the age, we also try to take into consideration the cosmic ray energy, which is also affecting the overall energy stored. Okay. And that is one of the reason why we need to know the precise location of the sample where the sample has been taken. So, apart from the alpha, beta and gamma, what we are talking about, the radiation source, okay, there is the minor extent is also been seen from the cosmic rays from the outer space. Okay. So, this is what we see, that there is some contribution of the cosmic rays also when the sediment is buried within that. So, surrounding we will see that alpha, beta and gamma, it will keep on radioactive material will keep enriching the lattice in form of the charges, but cosmic rays also will have some sort of an input in that. Okay. So, radiation energy trapped in crystal defect is stimulated in laboratory through TL or OSL method. That we will see how what are this OSL method what we are. And the OSL dating provides an estimate of the time elapsed since burial. This is what we have discussed, and basically it gives you the depositional age of the sediment. So, again it has been explained in a simpler way that once your sediment is buried, so it will keep acquiring the energy that is what we call ionizing energy is stored in the crystal lattice and built up over the time following the burial. Okay. So, after burial it will keep acquiring, and the sources coming from alpha, this is potassium, rubidium and thorium. Okay. And that is coming in form of the alpha, beta and gamma, and also what we were talking about, the cosmic rays. Okay. So, over the time this is what we usually try to get is the equivalent dose, that is DE, and then the dose rate has been calculated from the sediments, the same sediments, but through different method, that is what we call the gamma spectrometry, and we are measuring the concentration of this radioactive element, how much was the concentration of this in terms of the radiation provided to that. So, basically we try to measure the uranium, thorium and potassium. So, we and that has been taken as a dose rate. Okay. And this is equivalent dose. Okay. So, once you know the equivalent dose and dose rate, you can calculate the age. Okay. And how we are using this. So, the equivalent dose D is then divided by the environmental dose, that is the dose rate what I am talking about is your environmental dose. Okay. So, that you usually use the part of the sediments to determine the percentage of uranium, thorium and potassium, and that will give you the. So, how this we obtain basically the DE. Okay. So, DE is obtained by the using the grains. Mainly if you want to use the quartz, you have to use a particular method, but and if you are using feldspar, then there is a different, and this is what you are having. The dose rate is your environmental dose rate, what I was talking, the DO, or maybe you can say, and if you divide by, then that will give you the age in gray actually. So, OSL technique first proposed by Hattney, who used the light sensitivity electron trapped in commonly available minerals on the earth crust, that is mainly the quartz and feldspar. So, this is the overall process what we learn. It follows the three stages. Okay. So, one is what we have learned in the school time and all that, the valence band and so how the electrons are and valence band and conduction band and all that. Okay. And whether the electrons are in stable state or not, that also again are important here. Okay. So, first process here is your irradiation, then storage and then eviction. Okay. So, these are the three stages which is been followed. So, this is the valence band, and then up and you have the conduction band. Okay. So, the electrons, when they are irradiated, they move up. Okay. They went in are getting into the conduction band, but in between they have been trapped, and this trapped energy has been measured through your artificially stimulated illumination. Okay. So, irradiation, basically when the sediment is buried, the ionization radiation from the radioactive elements, that is what we were talking about, the alpha, beta and gamma, and the elements which we are talking about is your potassium, uranium, thorium, potassium. Okay. And the cosmic radiation ionize the crystal. Okay. This process is known as irradiation. So, this is the initial process what we are talking about. Then during an ionization, the electrons in the valence band here, okay, may gain sufficient energy to rise to the conduction band. Okay. So, they will start moving up, and once they gain sufficient energy. So, second is the storage. So, they stay in the conduction band for some time until these electrons are illuminated and release the energy in form of single photon light, that is your illumination. Okay. And then the third one is the eviction, that is the trapped electrons can be released due to sunlight, or you can say laboratory induced illuminations. Okay. And the signal initially decreases rapidly and then at a slower rate. So, this basically this is the process what we are measuring, okay, in lab, eviction. So, the bleaching part which we were talking about is that once once it is buried, it will acquire the illumination energy, and once it is exposed, it will bleach, and then this will be again like resetting will be done, and again it will keep growing. Okay. So, this is what we are talking about. So, sediment exposed from burial, bleaching due to the erosion, transportation and deposition. Signal rapidly builds up in the buried grains, mainly from the natural radioactive elements urium, thorium, potassium, as well as cosmic rays. Sediment samples is collected. This we will talk about, that these are collected without exposing the sample to the sunlight. Okay. Because sunlight is having higher energy and it will zero out. So, that is what we were talking about, the resetting is taking place. So, when it is exposed, it will zero out all the energy which has been stored. Okay. So, signal emitted from the mineral grains in the samples when exposed to beam of light is measured by photomultiplier tube. This we will talk about very quickly. Okay. Now, the resetting one, okay, let me just talk about. So, this is what we were talking about, the age, how we will calculate. Okay. So, we will get the D, that is your equivalent dose, and the dose rate. Okay. And both you will see that this has been mentioned in gray, but finally, if this has been done, then the age which you will obtain will be in years. Okay. But usually the D and dose rate will be in gray per year. Okay. Now, the OSL technique, usually what we do once the sample has been collected, how the sample is collected, that I will be coming in a few seconds in next coming slides. Okay. But one most important part which we have to take care is that the sediment should not be exposed to the sunlight. So, mostly we collect that in with the aluminum pipe, or maybe the GI pipe. Okay. So, this is the same thing which we have discussed in the previous slides, talking about the D and D0 here. Okay. So, that will give you the age. Okay. So, equivalent dose can be obtained by averaging the natural and the test dose information. Okay. So, D is measured in gray, where 1 gray is 100 rads. Okay. So, now environment in which the optical stimulated illumination can be applied on time scale, if we take, then it ranges from 1 year to almost 200,000 years. It has a very wide range. This is one advantage of optically stimulated illumination dating technique. Okay. Whereas carbon is having limitations, it will become like the ages will be having more uncertainty if we go more than 50,000 years or so. Okay. More than that. So, and then application here is extremely wide. Okay. So, you can talk about that the exposure age, nowadays people are talking about this. Okay. The exhumation age, how when the hills or maybe the rocky portion or the rocks were uplifted here. Okay. And many other applications which have been given here at different environments. Okay. This is mainly the coastal environment. In the fluvial environment also you can use this. Okay. And even the glacial deposits you can use for the dissolution activity areas where you are having the caves. Okay. Slope deposits, mainly the landslides and all that. Okay. Alluvial fans, active tectonics, sand dunes, you can talk. And even as I told that people have started using initially the archaeological site. Okay. And then this is all the marine environment. Okay, you are having, and the the desertic environment also you can use, and lacustrine also, lake deposits. Okay. So, you can use at multiple and very wide application of the OSL edges. Now, the sample collection mostly what we do is that if we collect mainly in the pipes, okay, or if the sediments are not, like if the coarse sand is there, massive coarse sand is there, then there is no issue, or fine sand. So, then you can collect in pipes, but if you are having gravels, and gravels, it will be difficult to collect the material in pipes, then we use the black tarpaulin, cover ourselves underneath to this, and then collect the matrix. Okay. But that the initial surface has to be removed while collection, because that is exposed to the sunlight. Okay. So, mostly we avoid this is what the pipe looks like. Okay. So, this we hammer this into the exposed wall from here and then get it covered. Okay. And mostly what we do is that, since we understand that this portion might have seen the light, because this was the portion over here, okay, of the wall, exposed wall. So, this is the portion which is exposed, and this was the last portion. While covering, this will also partly get exposed. Okay. So, this part we usually do not use, but the middle part is been used for normal processing. Okay. So, for OSL dating, mostly we use the central portion of the pipe. Okay. Then there are different processes what we do, that is chemical analysis and then magnetic separator, that I will come quickly. Okay. Before we come up with an pure quartz extracted from the sediments. Okay. So, the wavelength, basically why this is important for us, because for quartz mostly we are using the ultraviolet light and in the visible light with the wavelength of around 460 to 500 nanosecond. This is for the ultraviolet light wavelength of that. For feldspar we are using infrared light. Okay. And the wave which is having the wavelength from 900 nanometer to 0.1 centimeter. So, wavelength is pretty high here. Okay. Now, red light usually why this is coming in here, because the sediments, as we are talking, should not be exposed to sunlight, okay, but can be exposed to red light. The reason is that the wavelength is of course 700 nanometers, but the energy is very low. Okay. But sunlight will have high energy. So, energy will be higher. So, this will zero out, or we can say that this will like bleach the sediments very fast, or the energy which has been stored, it will be completely removed. But energy will not get affected, the trapped energy will not get affected if you are exposing that in the red light. So, all processing we do is been done in dark room, that what we call okay, and mainly this dark room is under red light. So, full sequencing we do is in the dark room, and that dark room is not completely dark room, but this is your red light under the red light. Okay. So, chemical treatment, initially removal of carbonates, we do one normal HCl and then wash the sample by distilled water. Then we also use H2O2 to remove the organic matters, this was for carbonate, and then wash the sample, oven dry, sieve, sample and magnetic separation mainly we do, because we don't want to remove the magnetic minerals. Okay. And then we also do HF when we want to use only quartz, and if we are sure enough that we have enough quartz, then we do HF, hydrofluoric acid is one, and then that removes your feldspar. Okay. Oven dry, check for the feldspar, use IRSL. So, even though if you do HF, there will be some leftover of feldspar, and that can like affect your measurements. Okay. So, the best way is that you again check IRSL, and if you find if there is some content of feldspar is still remaining, you do again HF. Okay. So this is what we do. As now, in order to have the quartz, basically we try to have the sieves of 90, and this is on microns, 125 and all that, and 90 to 125. And mostly what we do is that we take this range of the sediment sample available for the dating and further separations. Okay, I would say that. Okay. So 90 to 125 size is used for optical stimulations, and further the magnetic, and we pass through this material when we obtain, okay, through the magnetic separation, and that will allow us a non-magnetic portion extracted, and then we usually, this is the amperes which have been given for during the separation and vibrations what we do. Okay. Further, after the magnetic separation, again we go for hydrofluoric acid and removal of the feldspar. The HF is washed, and the remaining quartz is again treated and concentrated HCl to remove the byproducts and the reactions. Okay. After washing away the acid, quartz, it is then put into the oven on for drying. After drying, quartz is again sieved using the 90 micron sieve, and greater than 90 micron portion is collected separately in a small plastic tubes. Okay. So that has been used, and then for preparation of the helicoids. Okay. So this is your magnetic separation. So during the lab, we will show you this all these instruments, and finally then when we are talking about when the quartz is separated, which is greater than 90 microns and all that. Okay. We follow a typical cycle, and these are been done in the lab. Okay. So first we have not given any sort of an artificial dose. This is what we are doing, because when we talk about the dose which has been given artificially, then we are talking in terms of the radioactive dose. Okay. So here we allow this sample to go through or decay in terms of after putting he preheat the sample, and then the measurements are been done here, and then after that. So this is what basically we call the decay curve. So this is the zeroing out completely, all the sample, the energy has been, then when we put after the heat, we are putting we are measuring the through the photomultiplier tube. Okay. But when we apply the test dose, then again we follow this. Okay. So the test dose has been applied, then it will gain the energy, and then again we have preheated and measured. Okay. So this is what we call this is the sequence we run, that is measuring natural and regenerative illumination. This is measuring illumination sensitivity, and finally we are calculating when we are getting, that is you use the Lx by Tx. Okay. And then here you are using the grays what we have given, that is 5 gray, 10 gray and 30 gray, so on. Okay. So that will give you the curve, exponential curve, and then this is what Lx by Tx. Similarly, you are using the illumination and the test dose, and then you are obtaining this 3 points. So with this you will be able to generate a curve, and that curve will help, because this we know that at what was the first natural illumination we obtained. Okay. Where we did not apply any of such dose. Okay. And that will help you using this curve, that what was your equivalent dose. Okay. So these are the steps which have been given, and you will learn when we are talking about this thing. So this is what we are talking about, that this is your mainly the you will get this point. Okay. So this will be obtained if you are having so this is known, but this curve helps you in obtaining the D. Okay. So this is like a single helicoid regenerative cycle, that is what we call SAR, and so we go for preheat, then OSL, then test dose, and then preheat. So this is the test dose part which we are talking about, and this is the natural portion, okay, of that, and this is what we call the L1, and this is T1, or you can say Lx by your Tx. Okay. So you have multiple test run like this, that is what we call cycle, okay. And then that will help you in having the curve of different points, okay, and that helps. So, if you are having the natural, you can see that, and that will give you the DE. Okay. So, further if we look at so this is the part which we were talking about, the LI, or maybe you can say LX or T X, and then about the reader, where we are using mostly the two type of lights, that is your for this is for quads mostly, and this one is for Feldspar. So, we need to when we are using Feldspar, then we need to change the filter, and that helps measuring the Feldspar part. And mostly the Feldspar has been done in the fine grain, following the fine grain method, that we will explain you how we are extracting the Feldspar from the following the fine grain methodology. And this is what we call the cresol. Then this is the area where we put the disc, okay. So, the small disc have been prepared, where the sediments have been allowed to stick using the silicon, and similarly several discs are been prepared, and that are been placed, and then as I was showing you the cycle, we keep running those cycles and to have the generation of the curves, okay. So, this is the measurements usually what would do in different cycles, cycle 1, cycle 2, cycle 3. So, this is natural, and then we are applying the artificial dose from here. This is the test dose here, but this we are using as an for the regenerative dose, okay. So, that we use 10 gray, 30 gray, then 50 gray, and then again come back to the 10 gray, okay. So, that gives us the curves, and that is what we call the shine curves mainly. I will come to that, that is the decay curves also are there, but this is the final curves which we are using, which we get, okay. And these are the the different points which you have measured, giving the different dose, okay. So, we are measuring the illumination here, and then finally with the help of the natural what you are having, and then this curves helps you in getting the intersection here, will give you the mainly the DE. So, this is what we call the decay curve. So, in terms of the quads, mostly if this is quads versus Feldspar, and mostly the quads curves will decay like this, okay. So, initially, but it will slow down, and then finally it will become like this, okay. This plateau type, but the quads will decay very fast here. And if you are having the young material, then the curve will be something like this, okay. And if you are having Feldspar inclusion, then you will have, and that is what we call the impurity, and this is not good for measuring the illuminations, okay. So, we also take care of that the moisture content, and this has also been used in like moisture content has been used for in the calculation of the age. So, this we have to do, and then the dose rate measurements, either we are taking the dose rate sample in the boxes and keep for 21 days to stabilize the radiation, and then we use either the detector, that is the HPGE, and this is gamma spectrometer, and for measuring the uranium, thorium, potassium content, okay, mainly. And this will be used along with the cosmic dose, will be used to measure the dose rate. So, this is how the processing has been done in the lab. Here, this is chemical processing which we do, and one has to be very careful because we are using HF also, other than the other HCl and H2O2. So, and these are the what we call the Peach-in boxes. We have so different samples collected from different areas are been kept in this, separately labeled everything, and then for oven drive we have like for drying the samples we have the oven here, and then we also use the sieves, okay, sieving for that. And as I told that this is always this area remains in under the red light. That is what we call the dark room. This is the sieve shaker we are using, and this one is your magnetic separator. So this has all been placed in one single roof. So first the chemical analysis, then separation of then sieving, then again we put it in the magnetic separator, then again we sieve if required, and then etching has been done once through HF. Once we feel that still the quartz is there, that can be done, and finally we start preparing the, once the quartz has been extracted, we start preparing the helicoids. Okay, and this is how we use the silicon spray so that the grains are get stuck on that. So we put a very like few grains on this, and then try to prepare the disc, and then disc goes into this actually. Okay, so this whole system gets lifted and open up. This is what we are having, the radioactive source. So this is a radioactive source. This is photomultiplier tube, okay. And this is your high purity germanium HPGE gamma spectrometer, which we use for obtaining the dose rate, that is the measurement of the content of your uranium, thorium, potassium here. So dose rate is generally measured in gray per annum. In order to get the precise dose rate and less uncertainty, it is always necessary to avoid sampling within 0.3 meters. Okay, so this is usually when we are collecting the samples in field, we need to be careful about that. Okay, so dose rate is measured by with an high rate gamma spectroscopy. The energy of the gamma radiation emitted from a sample is the process of isotope undergoing decay. Okay. So this has been kept again at a very low temperature using liquid nitrogen, and the temperature goes because the electronics will then not work. Okay, so this is one of the point which we usually try to maintain, that HPG has been kept at a low temperature, that is your minus 96 degrees centigrade. So further, like grain size and the minerals, as we have already discussed about this, that mainly for the potash feldspar usually has an high OSL and IRSL sensitivity there, and they get bleached very rapidly, as I was showing the shine curves also, or the decay curves. So the feldspar will decay very fast, while the quartz will take time and then it will decay. Okay. So again, feldspar composition display an effect termed as luminous fading. So this will have this effect what we were talking here. Okay, and mostly if we are not we are having contamination, then we may end up having underestimation of the age actually. So if we are using quartz, then we try that the quartz the feldspar has been removed, okay, as far as possible. So hence quartz is preferred over because it is having, like, this is the reasons that you have fading, and then it has been observed that the signal decreases very fast as the samples and stored in the laboratory and the dose and thus so in anomalous manner because of the physical parameters of the trap suggest that it should be stable leading the age of under. So it is basically underestimation of the age will be there, but if you are using purely feldspar, then we change the filter, and then as I was talking about, that we use IR, and then we separate out the feldspar using the fine grain method. Okay. So this also I have discussed about the grain size, so I will just go ahead. Okay. And IRSL part also, infrared simulation signal is emitted when the mineral is exposed to infrared radiation, typically, and then used for dating mainly the feldspar. For OSL, light emitted LEDs with the peak emission, this is again what we have already discussed in earlier. Okay, but you can go through when you are getting the slides. Okay. Now, this is important, which I initially mentioned about that the optical illumination, why it is better than the C14 ages. The optical dating can be done for mainly geological sediments, sometimes fire potteries, bricks, etc. Difference between radiocarbon dating and OSL dating is that the former is used to date organic material, okay, while the later is used to date minerals. So, we are using the OSL to date the minerals, and this is for your 14C, okay, mainly. By analyzing coastal dune using OSL dating, it is now able to provide a better chronology for the past 300 years than the radiocarbon dating. For such fluctuations, 14C production caused large uncertainty when ages are calibrated. Okay. So, this is one of the reason is that this is having the half life of your 5730 years. Okay. Hence, reliable date can be obtained for the 14C up to 50,000 years, but if you see the OSL, it can go up to almost like 200,000 years. Okay. So, this is one of the disadvantage of the C14. Okay. And again, C14 is mostly been seen as an detrital material. Okay. So, it is transported, not the in situ one. Okay. So, this is one of the, and this, as I told, that it can go up more than that. Actually, TL can go up to like more than 5 lakh years. Okay. So, with this we'll end up here, and then as I told that we will come up with a lab. You will have the lab visit through like we will be showing you the lab through recording, and also we will be doing one lab on this. Okay. So, where you will have get an hand-on practice how we are calculating the age of any particular sediments. Okay. So, thank you so much, and I hope you enjoyed this course, and whatever queries you have, you can please contact us. We will try to sort out. Thank you so much.